So thank you very much for the kind introduction, and thanks for the invitation. It's really a pleasure being here. I mean, I have been to Aachen often. You know, a couple of friends are here. One is sitting in the first row, so old-time friends, right? So and to have the honor to deliver here the I think you call it the autumn lecture, right? So for the Center for Computational Life Sciences. So yeah, so the topic that I have chosen is Computational Respiratory Biomechanics, and the subtitle From Bench to Bedside, From Cradle to Grave, which means which should kind of indicate what we try to do is really from very basic scientific work to really translate it to the bedside. And from cradle to grave means not we bring you from the cradle to the grave, but kind of that aspects of our work are relevant for all stages of life, as I would say. Well, I was expecting, and I guess it's also true, a diverse audience from different fields, which is always challenging for presentations, right? So you try then to put together a presentation that pleases everyone, and you have to run the risk that actually it not excites anyone. So I hope I can do it differently, but I tried at least to put together a presentation that you know, should be hopefully contain interesting aspects from people from, I don't know, from medicine to computer science to mathematics to engineering and different life science aspects. And it will not be only on biomechanics. Biomechanics is kind of the, I would say, the vehicle that the focus point, so that we don't get lost. But I would start with a more general part first, so that is also relevant for people that are not interested mainly in the respiratory system. But let me start with some motivation from the respiratory side. Some motivation that kind of some of these questions came surprising to me when over 20 years ago we started working on the lung, you know, and I remember, I guess at that time, so this was a time when your Dean of Medicine was still in the very northern part of Germany, and we had, which was, I mean, one of the good things why I can report on such works was because I had the pleasure, and really I didn't deserve it at that time, that we could start with some excellent medical people that were open-minded enough to dare to talk to engineering scientists, right? I mean, it was Josef Gutmann and Stefan Uhlig. These were the two groups that we could collaborate. And I remember we started off, which I think I can recommend to everyone who is interested in such kind of work. We started off in traveling to Lübeck, and we had an afternoon where we explained each other what we mean when we say a certain word, you know, because when we say stress, what is it for us? And what do you understand with this word, you know? Because otherwise, it, also from experience with other collaborations, sometimes it takes years. You always think that you are expressing yourself clearly, but you don't, you know, because, I mean, in every community, in every discipline, you have a different understanding, you know. And I remember, I think it was an article even that you wrote with your wife, I guess, if I'm not mistaken, is, wohin geht die Luft beim Atmen? Wasn't it? If I'm not mistaken, I didn't look it up, but motivating. So, some questions. Why is it so challenging to improve treatments for certain lung diseases? What hinders truly personalized, optimal, in short and long-term treatments and ventilation strategies? And some further questions. Or to cite a very important statement by Gary Neiman and co-authors that wrote a review article, what is now 4 years ago. It's like where they claim that there has essentially been a stagnation over 2 decades in protective ventilation in acute lung injury, despite intensive research. You know, and so what hinders progress in the development of better ventilation also in neonatology? So for the very premature born babies, you know, and also I mean, a lot of people are looking forward to using inhalation therapies more widely for different diseases. Why is this not working better? So, so all these questions kind of can serve as a motivation for the work that we have been doing in the respiratory field now since more than 20 years. So, but before I go into that, let me start on some more general aspects. And well, with my gray hair and my age, I guess I finally can be able to even mention a little bit in my talks some of my hobbies, and I'm kind of an scientific enthusiast. So when I have some free time, I just study different fields of science, you know, philosophy or cognitive science or psychology or whatever. I mean, this is also nice, you know, in the Academy of Science, a lot of opportunities to talk to people from very different backgrounds. That's very nice. So let me give you some points. So first, it's sometimes people say, oh, you are just doing modeling, you know, you are just doing models, you know. And so I would say here, when you look here, so just focusing on the medical fields, you know, I mean, we have to be aware that models are everywhere, right? I mean, even if you look into the most recent developments and understanding of cognitive and neurological processes, how our brain works, you know, and I'm very convinced that our brain also works with models. It would just not be possible to process information and make decisions otherwise. You know, we develop models in our brain, and just the errors make us learn something and improve. So here, also for the experiment, right? I mean, some medical researchers, experimentalists, they talk about the mouse model, right? And every model that you do in an experiment, every investigation that you do in an experiment is a model. There is a model understanding of the question that you have. Of course, in simulation, we need a mathematical model, but also on the patient side. And kind of in between all these fields, there is modeling involved, and there's some information flowing between these different fields, and there is some uncertainty involved. And when you just split up, and as I said, modeling is omnipresent in everything, right? And well, you even could divide up the top picture in saying that, you know, even when you do in vivo experiments, it's also a model, because you design your in vivo experiments, let's say patient study, you design it based on some hypothesis that you have to model. Sometimes we make it very explicit that this is a model. Sometimes it's just kind of, we are not really aware of that, right? So what we mostly use is what some would call mathematical modeling and simulation, right? And there I would, without categorizing it, but just to making you aware that also their models are very different when people talk about models, right? So, so what we try to do is mostly, not only, but mostly what we call physics-based models or first principle-based models, right? But they are also very powerful and very good phenomenological or heuristic models, or what we distinguish the physics first principle-based models versus purely data-based models, you know. And as I said, it's not categorizing or a hierarchy of models. It's just we have to be aware about the difference of it, especially when we go from interpolation to extrapolation, or whether we want to be really predictive. And interpolation, extrapolation, I like to show this nice example from textbook mathematics, right? When people say, oh yeah, I have this data and I have a perfect fit, you know. I mean, here I have a very nice example that I sometimes also use in class, right? I mean, in reality, you have a function that is a second order polynomial, right? You do some measurements, it would be the blue dots. And now you have different approximations, right? So the yellow line is a polynomial of zeros orders, a very simple model, right? So then you have a first order model, you have a second order model. Oh, and then you say, okay, no, I want a perfect model, right? And then you take a ninth order polynomial and you have a perfect fit, right? I mean, this is the perfect model, but only for these data points, right? I mean, the extrapolation is here, even the interpolation is bad, not only the extrapolation, right? It's bad, and there is this nice saying from, I mean, some claim it based on, for John von Neumann, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk, right? So if you just have enough parameters, you can build every model, but it's not saying anything, it's not providing any new insight. So the point is, and this is something that is kind of very much misused, I would say. I often challenge my students and say, what is the right model for a car? You know, people talk about virtual cars. There are some initiatives which call virtual car. But if you look into the automotive industry, you know, the models that they have there are completely different. There's a completely different model for driving or for processing or for NVH or for whatever, you know, because in order to tell you what kind of model you need, you have to first formulate your question, because every model is only possible when you have a question. It's like your brain. We model reality. We don't even know what reality is. We have no way of finding out what reality is, you know, but we have a model because we developed certain senses just in order to survive, because certain things are important for survival. If we wouldn't have had these senses, we wouldn't have survived, and evolution would, well, created some other funny creatures, right, and not us. So it's very important. So when people now talk about, let's say, virtual physiological human, you know, I mean, don't believe the advertisements, you know. The point is claiming that, you know, well, we have the patient in the computer, you know, and we can just, you know, well, we can have the individual drug for this one person and so forth. Yeah, maybe on the long run, but this will be a very different model than, let's say, a model that defines about the success of a surgery or something else. You know, it's like a human is much more complicated than a car. And even for a car, we have hundreds or thousands of different models depending on the question. And the same is also, I mean, there is this word digital twin. I also use it. We also use it, you know. But you have to be careful. I mean, first of all, there's a huge misunderstanding, I think, all over the world, but especially pronounced, I would say, also in Germany still, you know. Many people say they call now, because it's funny and it's a buzzword at the moment, you know, when I have a simulation model, they call it, this is a digital twin, right? So, I mean, the modern definition of a digital twin is you have a virtual representation of a real system, and you have data flow and influence in both ways. So, one simulation model, I would not call a digital twin, and I think now there is a consensus now, at least at the top people, and there's a very nice report from the Association of Academies in the US that formulated this in a nice document, you know. So it's really information flow from the real system to the digital twin to update it, but also information flow from the virtual to the real world. So this is digital twin. And I would even claim that we are better than digital twins, because imagine you would have a twin and you are about to have a surgery and you want to see whether it's going and how this influences your life the next 10 years. And you say, well, my twin, anyhow, I don't like him so much, so I sacrifice him, so please do the surgery first for him. But then you would have to wait 10 years to see how he's doing, right? So this is not. So what we can do with computational modeling is we can do this now, right? We hope we develop the right models to predict even over, so we can be faster than time, so to say, you know? And the other thing is, we are not doing modeling in simulation just because we can do it, right? Which is sometimes in science dangerous, right? And people sometimes do it this way, but at least not for us. So for us, it has to bring novel insight. You know, we cannot just simulate in the sense of, you know, we can replicate something that is already measured. And this is why I had it from the first time when I started doing work in biomedical engineering. It was essential for me to always collaborate with people from the medical or biophysical or biological side to really be challenged to see whether we can provide information that is not there. because sometimes just you are very excited, you want to develop. I remember in the early days, I had a wonderful student, I mean, she was amazing, you know. We had a great idea on a model, and in the next meeting, I guess I mentioned it, and then I guess it was, if I'm not mistaken, it was Stefan saying, well, oh yeah, I mean, if it's interesting for you, fine, you know, you can do it. But for us, this information is not relevant for us, right? So we stopped it, you know, because, I mean, we want to bring insight and not please ourselves. I mean, time is too precious, right? So, and in my abstract, if anyone read it, I have written that, and this is also what I claimed when I was touring some of the top clinics in the US earlier this year, and some liked this title. I had it even in the title. It's kind of, I really believe that these type of things done in the right way, what you are trying to do also here in the Center for Computational Life Science, this can really cause a paradigm shift in healthcare. You know, and just to make sure, this is not bashing physicians or clinicians. You know, it's not saying, oh, they are not clever enough. I mean, we have to show them how to do things. No, not at all. Of course, this is not what we do. You know, but the point is just, well, like in many sciences, you know, it's how you approach certain things, right? So this is maybe a bit a provocative statement, but at least it's my observation also is when I'm at the Academy of Science, when we have these meetings and I hear people talking from other fields, I said, well, I think it would be interesting if they start trying to do it in a way that in my opinion, has made a huge shift in the engineering and natural sciences. If you think about before Newton, you know, what they have done, I mean, mechanics was always important, right? Because it was about how to cross a river, whether your roof or whether your cave sustains the pressure. I mean, it was observations and then making conclusions. Very clever people made the right conclusions, right? But then with Newton and others, they formulated it in a mathematical way, in a very precise language, right? And this made really a huge change, you know? And I'm not saying that we nowadays can model a body or any biological system in a precise mathematical way. But I'm convinced, and I hope I can show it, we can formulate some aspects of it. And this takes out some complexity of a very challenging job of physicians in the hospital that have to have everything in the mind, which is very, very difficult, right? So because often people say, oh, that's not rocket science in order to say, because that's not complicated, you know. I have the pleasure, I have worked in rocket science in the past, you know, and I also work with medicine, and I would say medicine is much more complicated than rocket science, you know, because, you know, look at, I'm not sure, maybe I should take this out because these are, well, actually, I can't leave it in because they are failures from someone who is gaining a popular position in the new US administration, so it's SpaceX, right? So in engineering, it's nice. When they develop rockets, what they can do, they can build one rocket after the other, they can test it, it fails, they learn from the failure, they build the next rocket, right? Try this with patients, right? Mrs. Smith, right? She's here. Oh, yeah, I replicate her. I tried. No, that was not good, you know. So Mrs. Smith comes again, right? So this is just not possible in medicine, right? And the other thing is like what people do in medicine, because they have to do it, is to do huge patient studies. And I thought, well, what would be if we would have to develop rockets based in a similar way, you know? And then I spent a night in the internet. This was during a tour when I presented lectures at different hospitals. I tried to adapt my presentations so that it fits more to the medical people, you know? So I picked up images of rockets that have been built, you know, in the last decades, you know? And now these are, I don't know, these are the first images that I found, right? And now imagine you have to develop rockets or the best rocket engine, you know, based on a study on all these different rockets. I mean, you can imagine what this means. But this is exactly what the medical people have to do, right? Because they never have two different therapies on the same patient under the same condition, right? So it's very challenging. So how can we improve this, and how can we also maybe reduce large animal patient studies? How can we really support clinicians to provide individualized healthcare? How can we provide unprecedented insights that allow them to make even better informed decisions? And one answer nowadays that comes immediately is like it's artificial intelligence, machine learning, because this solves everything, right? And I would like to, not because I don't like artificial intelligence, it's amazing, and machine learning is great, right? But just because I'm a bit frustrated that even some of the best scientists I know somehow lose all their criticality that should be inherent to every scientist, you know, when they hear about so. I would say it's a very powerful tool, but it's no magic wand, you know. So it's like it's not magic, right? So, and if I want to be critical or provocative, I would say it's a very powerful interpolation method, you know. I mean, of course, it's overly critical, but just to in order to base us a little bit, you know. We have to be aware that the data is never unbiased, right? So, I mean, if we would have used all the data before Kepler and Galileo and Ptolemaios, you know, we probably would have come up with a different model of the universe, right? So, we, at least to my understanding, maybe someone here knows it. I haven't looked it up the last few years, but a couple of years ago I tried. We still don't have convergent theory for machine learning or artificial intelligence. I mean, for simulation, we very much rely on convergence. So if we spend more effort in a simulation model, we get closer to reality. You know, when I talk to some of the top experts in machine learning and artificial intelligence, I said, no, we try to train a new network with more hidden layers and more whatever, you know, and then we see whether it's better. But, you know, you don't have a real convergence theory, you know. Sometimes too much data can also be bad. It's not just adding more data, which is currently a trend, you know. We just need more data. It also has some downsides. And some data is simply not there. And I have I'm sorry for this toy example, but just to give you what I mean with that. Let's assume you have the following task. You have to throw balls from one container to another without breaking them, right? So we have two containers. One is filled with balls of different types and colors and maybe sizes. I didn't find a better picture on that. And then the other container, and you throw it over there. And you make your testing, you know, you throw it, and then you see whether it breaks or not, right? And so you, over years, because you know you are a professor in, I don't know, Institute of Ball Throwing or whatever, you know, you examine everything, right? The size, the color, the weight, the surface roughness, the texture, the wind speed, the throw velocity, the throw angle, and the ground surface. And then you find out, statistically almost relevant, that the red balls are the best, right? So, which is kind of a random, I mean, the color definitely we know. The color has no influence usually on the problem is that, well, one thing that was not available for you was the material of the ball, you know. And it's very obvious when I have a glass ball or when I have a rubber ball, you know, this will dominate everything, you know, independent of the roughness, of the size, of the throw velocity, right? And this is often the situation in medicine, right? Certain data simply are not there because you cannot measure them, right? So, and the other thing is like when people say, oh, we just use AI, and I say, well, maybe it's just good not to ignore knowledge that we already have. Let's go now. The moonshot strategies are very popular. You know, there are books even in economy and even in law and so forth. You know, we have to have a moonshot strategy. Well, when we had to when the mankind wanted to bring the first person on the moon, you know. The idea was not to do artificial intelligence, which would be, well, just fire off hundreds of thousands of rockets and then use AI and we interpolate and see, oh, this one will hit the moon, right? And then when we want to go to a different planet, you know, we just do 1 million more of rockets. No. This was not the approach. The approach was we knew about Newton's laws. right? So we could calculate certain things. Of course, it was not perfect, and we had to test a few things, whether our predictions are correct. But then it was done, right? And the same thing is what we are trying to do for medicine. Not that we answer every question. It's far too complicated, but include what we know in order to really bring it to a different level, right? And this now, and I will not read everything here, this has a huge potential, how this can really help clinicians in their daily life. So, and this is what I really am convinced, whether I'm still experience this during my lifetime, since I don't know how long I live, you know, I cannot guess, but I'm sure, and I really hope that this will be brought to the table via younger people. And this is what I sometimes call individualized in silico powered medicine. Before now going to the respiratory, I'm sorry, sometimes I'm taken away by the subject, you know, I'm too excited, as you can see. So I want to briefly comment about uncertainties, because this is also often ignored, and I think it's very relevant for, especially in the context of medicine, but also for some other reason, you know. First of all, well, I see a lot, at least in computational biomedical engineering conferences, people, you know, they make one simulation of, I don't know, a cardiovascular system or whatever, you know, and then they make some conclusions, you know. I mean, no reasonable physician will buy this, right? Because we know, well, how reliable is your prediction? How reliable is the information that you give me, right? I mean, they are really trained to work with statistics and with uncertainties, because there are always uncertainties. I mean, it depends on what this patient had as breakfast, you know, how certain things are a few hours later. So we have to be aware. First, we have to include uncertainties. So this is why in recent years, we have spent a lot of work in uncertainty quantification. I mean, of course, we are not the first ones doing this. I mean, there were a lot of work done. Actually, my previous life, so before I went to Stuttgart, I was in Princeton for a while, you know, and in my first academic life, I was working in the field of reliability theory and stochastics and so forth, and also partly in Princeton. But then I was a little bit frustrated in the sense that, well, yes, these are very nice approaches, but the models that they had there were just not good enough. So they were even bad in predicting the mean value. So then what about uncertainties there? You know, if the mean value is already wrong, I mean, the distribution is not so important, right? So I left it. But now I came back, and we, over the last couple of years, with some excellent co-workers, we developed novel approaches how we can do uncertainty quantification even for complex, large-scale, non-linear, time-dependent models. And we have worked on global sensitivity analysis to really find out what the important parameters are. And of course, in a similar fashion, the inverse analysis, and a lot of the work in inverse analysis in many years, not all the work, of course. I mean, there was some fantastic work also in the past, but a lot of work approached it purely in a deterministic way, which caused mathematically an ill-posed problem, you know, because actually the model is never 100% correct, the data is never 100% correct, so there often is no solution to your question. But once you approach it in a probabilistic way, it's a well-posed problem, you know, and it even offers some additional benefits, and some things that we do there as what we call multi-fidelity analysis. The important thing here, a message that I want to give here to people is, so this is even interesting to people that are not interested in simulation at all. So it's also for people that only do experimental work or only do clinical studies, only, I mean, you know what I mean with that. Because it can give you all these tools can give you information on where to do it, where to spend your effort. The other thing is it has also potential for the real digital twinning, because these uncertainty quantification and inverse analysis is exactly these type of methods are necessary for really efficient digital twins, for the interaction between the real and the virtual representation. And the nice thing is also these approaches allow you to learn how much you have learned. So this is what I want to show before going to respiratory, to a very short excursion to another topic that we have done, which is oncology. Some work I only very briefly couple it. I mean, it's clear that, and I think it has become clear in not too long ago, that physics plays a crucial role in cancer. Right? And in the US, because of that, they founded the Physics Cancer Institute or something like that. So we also a couple of years now work on tumor oncophysics, what we call it, and we've developed a very novel and unique system for solid tumors, including all the different ingredients. I will not go into detail, but these models are complicated, but for us it was very important to have all the parameters that are involved there are really physics-based. They have a physical meaning, but they are many. Right, so then we had done some for a certain project that we have done together with a group in Zaragoza that have done some microfluidic experiments for neuroblastoma at that time. We tried to see, we have done for this, we have then global sensitivity analysis, and we identified the 5 most relevant parameters that influence it. So that really had impact on how fast these tumor for these babies are growing. Right? So and the others we could keep at the population average level. And then they have done some microfluidic experiments in Zaragoza, and we did the measurements. And this is a nice thing what I wanted to show about. We learn how much we have learned, because here. This was the result. So these were the 5 most important parameters. These are the ranges for these parameters that, through the reasonable and study of the literature, where the parameters would lie. And we wanted to identify which are the real parameters for these tumors that we have in these microfluidic experiments. And when Sylvia and Barbara came back with the results, they were very, very frustrated, because they said, well, you see, because these are the probability distributions after we included all the measurements, right? And say, okay, well, we have no clear value, because, I mean, especially if you look like, let's say if you look here, I mean, it's almost the same probability that this is the value that needs to be included in order to describe what's going on, But I was completely excited, and meanwhile, I think I could, my excitement spread over to my coworkers, so they are also very proud of the work now, because this is exactly what we want to do with serious science and with serious simulation, because if you would do a deterministic parameter estimation, you take the values, and you would just have maybe you would have selected this parameter. It's not the worst, but it's also not the right one, right? And here, some other parameter, but here. We could show how much we have learned by these measurements. And what we learned is, we have not learned enough. But we included all the information that are in these measurements and that are in the model. But the measurements were not enough, and this is what we so often miss, that we include some data points and then we make a prediction on a value, but we have no idea about how reliable is this value. Was it just a lucky shot, or was it a real information gain that we could have? So now let's go to, so these are just, I already mentioned oncology a little bit. So these are the fields in biomedicine that we have been working on in my group over now, well, many years. So you see from very different level, from subcellular to cellular biophysics, but the last 6 areas are more like on the organ or really disease scale. And the one that I picked is respiratory biomechanics, as you saw from the title, and it's also the one where we are closest to really clinical application. So, well, I'm sure everyone who works on a certain organ will say it's an amazing organ, because I mean life is amazing and our body is amazing, but I kind of I really got excited working over years in the lung how amazing this organ is. And another, I hope I can stop now then, but I learned a lot from Stefan Uhlig, and one thing that he told me early on was that, well, an engineer would never design a lung like this. And he was right, because you want to have a cooling apparatus in a car, you have an inflow here and you have outflow there. But I mean, which engineer, would design a lung where you have to transport oxygen down more than 20 generations and CO2 out through one pipe? It's vulnerable. It's crazy, I mean, because you cannot empty the whole lung. So how should it even work, that the oxygen goes down and the CO2 goes out, right? But I'm not claiming that whatever God or whatever evolution was a bad designer, but it was like that probably we don't understand the target quantity well enough, right? I mean, if you look at birds, the bird's lung are more like an engineer would design it, right? It's really going one way through, well, all of you probably know, so you have one trachea, then you bifurcate, you have 5 lung lobes, and so because on the left side you also need some space for the heart, those people who have one, and you have more than 20 generations, and then at the very end you have the alveoli, where the blood, so the exchange of the gas with the blood takes place. These pictures are always in the medical books. I'm still surprised why. They always look like this, and it's clear it doesn't look like this in reality, right? Because it would not work. I mean, this looks more like grapevine, right? So, but it's not like that, because at the end you just need a maximum surface in a certain volume, so it has to look different. And then we operate it very nicely, and in reality it looks more like this. So it's like a sponge that is, every cell in the sponge is opened up just from one direction, right? A very interesting thing. And then of course the composition of the walls is very different. From here you have even cartilage in the wall, very thick wall, down to the alveoli, which has to be very thin, because oxygen molecules and CO2 molecules have to transfer through the wall, to go from the blood to the lung. And the whole lung is lined with liquid and also with some surface active agents. Right, so this is more than 20 generations. We have a grown-up individual has roughly like 500 million alveoli, and this is, for example, some testing. These are lung slices that we got from Stefan Uhlig's group, and we did a lot of mechanical testing over years. So it's really very thin walls and very vulnerable systems. So now, to follow my own advice is like, well, why would we model the lung? So, I mean, just because we can? No. So, I will show one application very detailed, like the left one, which is from anesthesiology and ARDS. The other one I just will very briefly mention to see that there's a wide application. Of course, here I need to be honest, I need to disclose that some part of the work is also transferred to clinic in the moment, or since the last few years, and for this part of the work, which is not purely scientific, I have to disclose that I'm co-founder and CSO of the company Ebenbild that is bringing this to the clinics. So why are we doing the simulation? Well, the simple thing is that this is what we heard from a lot of medical people. The lung is a black box, So these are some citations here. So one from the head of internal medicine intensive care in Innsbruck. This was at the beginning of the pandemic, when we started our company. There was a press release, and he was interviewed whether this would be irrelevant, and he said, well, we cannot know at all how different parts of the lung behave during mechanical ventilation, and this could, if this works, it could be a game changer. And in a paper by a couple of people, top people in the US, in 2017 in Journal of Applied Physiology, it said it's essential to understand the impact of a mechanical breath on the microenvironment. But the problem is we have no method to see what's going on in the lung while breathing or while ventilating. No imaging, no measurement at all, so it's really a black box there. And our idea was to open this black box. This was our goal. So here, what you see here is a COVID lung. So you see these different infected areas. So it's very typical for COVID, right? So and I digged out an old graph that we had when we started collaborating with Josef Gutmann and Stefan Uhlig and in this kind of Schwerpunktprogramm. So I think this is an image from, if I'm not mistaken, I don't even know where it was from. Maybe it was from Josef Gutmann. It's like, he explained, like, say, here is the whole lung, right? And we only can measure here, right? At the ventilator, right? So and then we had, but we would like to see what's going on at the alveoli, And so our idea was to develop a comprehensive computational lung model to provide this insight, to provide this magnification class. And then, this is also work that we have done here with Stefan's group, and then we can look at what these local mechanical states are doing with the cells, and this was a paper that we had together many years now ago, right? So, if you, I don't know, it was a couple of months ago, I was interviewed by some I don't know, was it from TV or I don't know which some journalist, about this work, and he didn't understand the complication, and then I tried to come up with an explanation, and my co-workers are still teasing me with this, because actually this was the part that he took out of the interview. You never know what they are taking, and I tried to explain it with some balloon. If you have kids, there are these figure balloons, like a rabbit, and my challenge was always, you blow it up because the kids want to see the rabbit, right? And then the question is, well, blow it up and try so that the ears go out, which sometimes is difficult. But at the same time, it should not rupture the balloon, because then you're bad dead, and they are very, very, they are very frightened, right? So, and then I said, and everyone understands this because probably everyone tried it, And now I said, well, imagine you have a balloon with 500 million ears, and this balloon was lying on the back of your car while you parked it in the sunshine. So some of these ears are maybe not so intact, not so elastic anymore. And now you have to find the right way of blowing in air on one tube so that all the balloons are used, or all the ears are used, right? Without any rupturing anything. And then they say, okay, this is exactly the topic and the challenge that the physicians have when they ventilate the lung, right? Because these thin walls shouldn't rupture and so forth. So what our lung model tries to provide is bring insight into relevant states of the lung under certain conditions, and also be able to test alternative strategies. So what can never be done in usual medical environment, because you never have two replicas of the same patient, right? So here you can test, I don't know, 20 different ventilation parameters and see what is this doing with the lung, right? So when the lung is a black box, what we usually can see is like, well, you see from the CT, on the left side you see an ARDS lung, on the right side you see a healthy lung. This is what you can see when you have a CT. And this is what usually is taken when you have acute lung injury or acute respiratory distress syndrome, right? So in order to develop our models, well, we needed to use all the nice about mechanics that we know and we love. It's like solid mechanics or tissue mechanics. We need fluid mechanics. We need transport mechanics. All this we did, and I could show a lot of equations and a lot of models and papers that we have done there. We have done some experimental work. This was a joint work with Stefan Uhlig and Christian Martin here in Aachen about identifying constitutive laws of this lung tissue, viscoelastic properties, volumetric properties, and so forth. So a lot of work in order to find the right material models for these parenchyma. We used the interaction of the airflow with the lung. We developed reduced dimensional models, because at the end we wanted to do it bedside, right? So we cannot, I mean, usually hospitals don't have a supercomputer in the basement. So we had to be fast, you know, so to deliver the answer within seconds or minutes, right? So, I mean, we have done a lot of high performance computing. So if some computer scientists are here, we know how to do this. So this is, for example, I guess we have probably one of the fastest, if not the fastest CFD solver developed in my group. So here we can, this is already a few years old, this slide. So we had a full Navier-Stokes solver where we could solve more than 30 billion degrees of freedom, one time step within 0.1 second, you know, on the SuperMOOC in Munich. So we really could scale it over 300,000 cores. So we know how to do supercomputing, but this is not what you want to use for clinical applications, right? So we had to do this reduced order modeling. So over the years, we have developed very different models, depending, as I said before, depending on the questions you want to answer, to provide insight, to allow to develop the reduced order models that are later needed, and with all the complications. So some of the applications that we have done, one is from neonatology, where we were asked to help a little bit with this high-frequency oscillatory ventilation, and this is collaborative work with the group in the neonatological group in Großhadern, south of Munich, so the LMU Klinikum, so Andreas Fremmer and his co-workers. So they wanted to understand why this works, because it was used, it was successful, but nobody really understood. And there was a paper which from Slutsky that kind of hypothesized what the phenomena are, but it has never been shown. And so we have done some very highly resolved, purely fluid dynamic and a simulation with transport of gases in the fluid to see why this works. And we have done this for some baby lungs. And also to see how this ventilation then the parameters influence. And we are actually currently working on a new project where they plan to do high-frequency ventilation for breathing supported. So when the baby starts breathing on her or him, his or her own, then how you can optimally support this with high-frequency ventilation. And you cannot do it in any way. So they really came back to us and say, well, could you help us? Because, I mean, we cannot test it with the babies. There's no animals models on that, you know, so can you give us a hint with your simulations on what would be the best for the babies so that we start doing this? Another application that is mostly done on the company side is inhalation therapies, where we have done some very highly resolved simulations on aerosol delivery within the lung and seeing where aerosols, depending on the size of the aerosol, on the time when it is administered, how these aerosols end up in certain regions of the lung. And fortunately, I got access to some data. There was one some couple of years ago, a group in the UK together with some other partners like Air Liquide in France that were allowed to do a study with healthy patients, not healthy patients, with healthy subjects, where they could do inhalation studies with some radioactive particles or aerosols, and then they did some SPECT imaging to see where these aerosols ended up. And we used this data in order to validate our model, and the results were amazing. So we could really distinguish here between, you know, left upper lobe, left lower lobe, right lower lobe, right. So how in the different, so the reference is blue, the simulation is yellow. Then in the different areas, and also in central and peripheral, where the aerosols kind of ended up being. So very nice. But the main driving force was really what we started more than 20 years ago, was kind of protective ventilation of ARDS patients. So for those of you who don't know about acute lung injury or ARDS, so it's caused by a lot of things like pneumonia, sepsis, trauma, aspiration, and since a few years also by COVID. You know, also most people that died from COVID died from ARDS. And it has rather high mortality, and the problem these patients need ventilation, and there is a problem of this, what is called the ventilator-induced lung injury or ventilator-associated lung injury, right? So damage of the lung caused by ventilation. And there are mainly two effects. It's volotrauma, which means when you try to ventilate the patient, because this lung of these patients is very heterogeneous, so that if you put some pressure, you're distending and overstretching the healthy regions of the lung. And the atelic trauma comes from closing and reopening so if you ventilate and you know you have a liquid lining when it's collapsing, and when this is going up, it can be shown very nicely. Also, they have done some nice experimental work and simulations. So there are very high pressures and stretches on the cells that line the airways. So the idea was to develop lung protective ventilation strategies, and there was a famous study published in 2000 where they changed one parameter and they changed mortality by double-digit percentage, right? So there is much to gain there. But the problem, so this is ARDS network study published in New England Journal of Medicine in 2000. So, but as already said, a stagnation over 2 decades. So, and the problem is we just don't have the local insight, and this is what we wanted to provide. So what we have done and developed was a method where we start from the CT scan, we segment the lung, which is rather, so the outside of the lung is rather easy to segment. The different lobes are quite difficult, but we now, with machine learning and artificial intelligence, we can do this fast. So the first models that we used for our first publication on that, I think my PhD student spent a couple of weeks for creating the first model. Now model creation in the company is done within seconds, less than 1 or 2 minutes maximum. Right? So then we have developed an algorithm that grows the airways in regions where we don't have an imaging, but which is morphologically correct based on the data of Weibel and others. We have these reduced dimensional models. We have also reduced dimensional models for the respiratory zone. And now the important thing is, so when we do this, so here you see a CT scan of one patient, your segmentation tree growing. So here this is an acute lung injury, you see the damage part. We have the computational lung model. And for this paper, this was the paper that was published in Journal of Applied Physiology in 2017. So what we used for parameterizing the model was one recording of a breath, so one breath cycle. So we are not changing the parameters in order to fit our results to the real data, because this would not give us predictive value and no insight, because then we have the data. So what we have, for us it was, is our model so correct that we can predict things without adjusting parameters? So all this data that you see is just here. It was a recording of measurements on the ventilator, pressure and volume, for one breath. This was the individualization. And these were the global data, so the tidal volume, so it was pressure controlled, and this was the tidal volume that the simulation result delivered compared to the measured quantities. But in addition, what could be done? Well, we now also have the local state of the lung, right? So we saw that it's very, it's very heterogeneous how the straining of the alveoli or the terminal units is. Right? So it's not homogeneous, and if you would do a homogeneous distribution of the different volume of the lung, then you would end up with a value like, let's say, 1.48, and some people claim that this is below where it does some harm, and 1.9 would be clearly above it, right? So it's very important. But well, then we said, okay, but maybe we were just lucky. We got the global quantities right, but who tells us whether the local quantities are right? So we have to be very self-critical, because nothing that we can compare with. And this is where we came across with electroimpedance tomography, which is a tool that is used in a couple of intensive care units, which is, many of you know, and Professor Leonhardt is an expert in this field. And so what they use is like it's a belt or whatever, a small jacket around the chest with some electrodes, and you provide some current on 2 electrodes and measure on the other electrodes, and you you vary these electrodes around with 100 hertz or something, and since air is a good isolator and water is a good conductor, right? You can reconstruct where you have air and where you have more air or less air. And this is kind of some of the images that you can see. You see, okay, so aeration on one side and less air on the other side. So if you would use this data in order to parameterize your computational model, you can claim everything, right? Because, I mean, you just need to, well, it's so coarse that you would not gain anything. But what we did was, we did not use this. We used out a virtual model, then we created a virtual EIT, we predicted what will be seen with the EIT, and then we compared it with the real images on the patient, right? So we created a virtual EIT here, so we did some work on, and we really simulated the patient also with the torso, with the electrodes and everything. And then we did the same reconstruction that was used in the EIT machines, and we could compare the computational EIT image with the EIT image on the patient. And this was a game changer also for our medical partners, which at that time was the group in Kiel, so Norbert Weiler, Tobias Becher, Ines Frerichs, who then, because I think before they always had, oh, we do some funny post-processing of the CT image, you know, so this was their understanding, but so that we really could predict. And meanwhile, we have done also a larger study with a lot of patients that we recruited in Kiel, and the comparison is quite good on different measures. But I will go over this, not to take too much of your time. So what we try is now we provide insight on the micro level. So we build a model based on CT. We enrich or enlive or functionalize it, you know, and then we can post-process it in the sense that we, for example, can get local strains or whatever is currently fashionable in the medical community. So in recent years, mechanical power was very much in the papers that being very relevant. I mean, for us, power is just a different post-processing of the quantities that we calculated. You know, we can have work of breathing, mechanical power, whatever. You know, we are in our tool for the company. We try to keep it open for the FDA approval because, you know, depending on what is the fashion in the medical community, what they believe in, the different, because I think the dispute is also so big because they don't know they don't have the truth, they don't have the quantity. So it's kind of a very vague quantity that they find some correlation. Once they have these local quantities, it's sorted out much more efficiently. And the idea is that then you have bedside, you have a monitor where you can see what is the state of the lung when you have changed your ventilation parameters, so that the medical doctor, not our tool, makes the decision about ventilation, but the medical doctor makes the decision about ventilation, seeing what the different ventilation settings are doing. And in recent years, so these are publications last year, I think I'm almost going over time, so it's close to 1 hour that I'm talking. I do this very fast. So we also extended these models, including recruitment and de-recruitment, so which is kind of here, both recruitment, de-recruitment on small airways, so collapse of small airways, but also another approach where we have alveolar recruitment and de-recruitment. So these were some papers that we could publish last year, so where we can also show, depending on the recruitment maneuvers that people do in the intensive care unit, so you increase the pressure for a while, but then the problem is when you go down with the pressure, does the region of the lung stay open or not? First of all, is it opening when I increase the pressure to a level that is still I can justify? And then how far can I go down so that it does not collapse again, right? And this is exactly what we can show now. And the most recent work that we are currently working on within my ERC grant with an amazing PhD student, Lea Kögelmeier, it's now, we couple this with the pulmonary circulation. So where we also include the blood, so the coupling of the pulmonary circulation with the lung, because at the end, this is completely interdependent, right? Because if you have some water in the lung, then of course there is no gas exchange there, right? If you put more pressure, this also will squeeze, so the heart has to pump more, and it gets less through. So this influences the parameter, and also this can be then coupled to to our heart model that we developed over also in the last couple of years. So the idea is really to include also the smaller blood vessels and in a discrete way, and in a homogenized way in the larger blood vessel in a discrete way, so like it is sketched here. And this is just a very recent example. So you have the CT image, you have the standard airway generation that I have shown you before, and now we also have the generation of pulmonary arteries and veins, you know, which is then here. And then you can here layer just, this is a very recent simulation, so done earlier this year. They used it for one lung half, so I think this was the right lung half, you know, and then you can show, and then we applied, let's see, a certain ventilation maneuver, and then you see how this is distributed over the lung. And with this, I'm closing, and thank you very much for your attention. If you're interested in any details that I skipped, I'm here. So I'm happy to talk about the details, but I used the full 60 minutes that I was told, and so thank you very much for your attention.